Alright, let's move on to question 2. In the gas phase, aluminum chloride is a molecular substance. A reaction of gaseous aluminum chloride at high temperature is represented by the following balanced equation. A, how many grams of chlorine can be formed from 125 moles of aluminum chloride? We know that aluminum chloride and chlorine are in a 1:3 ratio. So for every 1 mole of aluminum chloride that you react, you're going to get 3 moles of chlorine gas. So let's first convert our 1.25 moles of aluminum chloride to moles of your chlorine using that conversion factor. So 1 mole of Cl3 is going to produce 3 moles of chlorine, and we want the mass of this. So let's multiply by the molar mass of chlorine. Oops, that should be Cl, my bad. And the molar mass of chlorine is 35.45 grams. So if you do out the math on that, 1.25 times 3 times 35.45 is about 133 grams, and that is your answer for part A. Let's go down. Additional reactions that involve aluminum or chlorine are shown in the following table. Okay, we have 3 reactions. B, calculate the value of your change in enthalpy in kilojoules per mole for reaction 1 above using reactions 2, 3, and 4. So this question is testing your ability to use Hess's law. So we need to find a combination of these 3 reactions that result in our overall reaction above. And remember that reaction was aluminum chloride decomposing to form aluminum gas and 3 chlorine gas atoms. So we need to find a combination of these 3 reactions that produces this. Well, the first thing that we can see is that the only reaction that has aluminum chloride is going to be reaction 2. But reaction 2 has aluminum chloride on the product side, but we know that we need aluminum chloride on the reactant side. So we're going to need this reaction, but the inverse of it. So let's take the inverse to form aluminum solid plus 3/2 chlorine gas molecules. And so this, the enthalpy of this is just going to be the negative of what we're given, because remember we flipped this reaction. So it's going to be 583 kilojoules per mole. All right, we have one of our compounds down, but the other 2 are still wrong. One thing that we can see from equation 4, our reaction 4, is that we can produce our chlorine from our chlorine gas. We can form the atoms instead of the molecule. So how do you get rid of 3/2 of chlorine gas? Well, what you can do is you can take this reaction and multiply by 3/2. So we can have 3/2 chlorine gas, the molecule version, to form 3 chlorine gas atoms. And the delta H of this is going to be 3/2 times the value that you're given. So 3 divided by 2, and that times 243 is 365 kilojoules per mole. All right. Now what we've done is that we've canceled out the chlorine molecules, and we have the 3 chlorine atoms. But our phase is still wrong for the aluminum. We have aluminum solid, but we need aluminum gas. And that's solved by our third reaction. Our third reaction we can use as is. And what that reaction will do is that it'll take that aluminum solid and convert it into aluminum gas. And the H of this, the delta H of this, is going to be 326 kilojoules per mole. And so if you add all this up, you realize that your chlorines, your molecules of chlorine cancel out, your aluminum solid cancels out, and you're left with what you need. So that's aluminum chloride gas decomposing to form aluminum gas and 3 atoms of chlorine gas. So what's the overall delta H of this? Well, we're just going to have to add up all of these individual delta H's. So 383 plus 365 plus 326, and that is 1,274 kilojoules per mole. And that is your answer. All right, let's go down. see a potential energy diagram of chlorine, the molecular gas, is shown in the following graph. One, based on the graph, what is the bond length in picometers for chlorine? Well, from a graph of internuclear distance versus energy, you want to look at the point where the energy is the least. And the energy is least at this point, which is around 200 picometers. And I'll take a second to explain what this graph means. So at this point, at 200 picometers between these chlorine atoms, that bond energy is going to be the least. If you go above that, then your energy starts to increase until it reaches zero. The zero is easy to explain, right? You can imagine two chlorine atoms that are super infinitely far apart, then they're gonna feel no attraction towards one another. But as you bring them closer and closer, their energy is negative. What that means is that they face an attraction, and they face that attraction until you reach the point where that attraction is minimized. If you bring them closer than that, so if you brought these chlorine atoms even closer, what would happen is that they would feel positive energy. And positive energy just means repulsion. So negative energy is attraction, positive energy is repulsion. And as you can see, if you bring them really close, then the energy just goes up infinitely. So it's really hard to bring these closer than they should be. So that's just what this graph means. Let's move on to 2. A student finds that the average aluminum chloride bond length is 220 picometers and the average bond energy is 425 kilojoules per mole. Draw the potential energy curve for the average aluminum chloride bond on the preceding graph. Okay, so let's draw this on the same graph. We know that the bond length is 220 picometers, so that's going to be about here on this grid line. And the average bond energy is 425 kilojoules per mole. So that's going to be about here. So that's where our minimum is going to be of our graph. And it's just going to follow this a very similar shape from the chlorine-chlorine bond. So let's just draw something similar. It's going to dip here and then pull back up and asymptote towards zero. That's my best attempt. But yeah, that's about what it's going to look like. Let's move down to D. 3 proposed Lewis diagrams for the aluminum chloride gas molecule are shown. In the aluminum chloride molecule, if the aluminum chloride molecule has a trigonoplanar geometry, which diagram 1, 2, or 3 can be eliminated based on geometry? Justify your choice based on Vesper theory. All right. If you look at diagram 2, diagram 2 is going to have a steric number of 4. The steric number is just the sum of all the bonds and the lone pair. So it has 1, 2, 3 bonds and 1 lone pair. So its total steric number is going to be 4. So if you look at a chart, steric number is 4 and it has 1 lone pair. That means that this is going to be a trig pyramidal shape. Diagram 1 has a steric number of 3 and 0 lone pairs, so that's going to be trig planar. And diagram 3 is also going to have a steric number of 3 and 0 lone pairs, so it is also going to be trig planar. So we can eliminate diagram 2 because it's going to be trig pyramidal. So obviously on the test you won't have a diagram like this, so is your only option to memorize everything? I mean, that is something you can do, but I think if you think about it logically, you should see that diagram 2 will not have a trig planar geometry. If you look at diagram 1, the shape in diagram 1, if aluminum has 3 bonds attached to it, and that's all it has, well, the molecule is going to be like, how do I evenly space out all these atoms? And the logical way is to have bond angles of 120 degrees. And 120 degrees is corresponds to a trig planar geometry. It's the same with diagram 3. The only difference is that now you have a double bond on one of them, which doesn't change the bond angle. However, in diagram 2, what happens is that you have these 3 bonds, but they get slightly adjusted because you have a lone pair on the aluminum. So that lone pair is going to have an effect on the chlorine. So you can see that in the diagram here. Those lone pairs are going to kind of push those other atoms down, which means the bond angle is going to be less. It's going to be about 109. So you can also think of it that way if that helps you. Let's move on to 2. Which of the 3 diagrams is the best representation for the bonding in aluminum chloride? Justify your choice based on formal charges. If we go back to diagrams 1, 2, and 3, I guess 1 and 3, since we kind of crossed out 2, let's calculate the formal charge on these on all these atoms, right? So remember, your formal charge is going to be equal to valence electrons minus your lone pair electrons plus 1/2 bonding electrons. So let's calculate that for aluminum in diagram 1. Aluminum has 3 valence electrons, usually, most of the time. Aluminum has 3 valence electrons. How many lone pair electrons does this aluminum have? 0. And how many bonding electrons? It has 1, 2, 3 bonds, so that's 6 electrons. 1/2, that is 3. So your formal charge on this aluminum is going to be 3 valence electrons minus 3, which is 0. And then the rest of the chlorines, while chlorine has a formal charge or valence electrons, it has 7 valence electrons. How many lone pair electrons are on this chlorine? It's going to be 6. How many bonding electrons? This has 2. So 1/2, that is 1. 6 plus 1 is 7. 7 valence electrons minus 7 is 0. I hope that wasn't too confusing. So diagram 1 has formal charges of 0 all around. So diagram 1 is looking like a very strong candidate. Let's just check out diagram 3. In diagram 3, you have aluminum. It's still going to have 3 valence electrons, but now you have 1, 2, 3, 4 bonds per se. So that's 8 valence, 8 bonding electrons. So 1/2 of 8 is 4. Aluminum is going to have a formal charge of 3 minus 4 this time. So it's going to have a formal charge of -1. Okay, so the chlorine here is still going to have 7 valence electrons minus the lone pair electrons, so that's going to be -4. And 1/2 the bonding electrons, it has 4 bonding electrons, so 1/2 that is 2. So that is going to have a formal charge of +1. And these chlorines just have a formal charge of 0. So what can we take away? Well, diagram 1 has 0 formal charges all around, and diagram 3 has a negative and a positive formal charge, and we want to minimize formal charges altogether. So diagram 1 is going to be the best representation for the bonding in aluminum chloride. So diagram 1 is the best representation for the bonding in aluminum chloride because all the atoms have a formal charge of 0. Now, diagram 1 might have confused you because in diagram 1, the aluminum does not have a complete octet. Diagram 3 does show aluminum with a complete octet, so you might be inclined to pick diagram 3 over diagram 1 just based on the octet rule. But aluminum is one of the exceptions to the octet rule. Beryllium, boron, and aluminum can all have incomplete octets. So they can have 3 bonds instead of 4. So it's just it's nice to know that these 3 exceptions do exist for incomplete octets. All right, let's move on to part C. Aluminum chloride is known to dimerize reversibly in the gas phase. The dimerization equilibrium is represented by the following equation. Dimerization is just like 2 of them combining to form one bigger molecule. So E says write the expression for the equilibrium constant Kp for this reaction. Remember, Kp is going to be based on the partial pressures of your molecules instead of Kc, which is the concentrations of the compounds. So Kp is going to be the partial pressure of your product, so Al2Cl6, over the partial pressure of your reactants. But the reactant is going to have an exponent of 2 because it has a stoichiometric coefficient of 2. So that is your Kp expression. Let's go on to the last part. A particle level diagram of an equilibrium mixture of aluminum chloride gas and Al2Cl6 at 400 degrees Celsius in a 25-liter closed container is shown. Using the particle level diagram, calculate the value of Kp for the reaction if the total pressure in the container is 22.1 atmospheres. Let's rewrite our Kp expression. That's going to be the partial pressure of Al2Cl6 over the partial pressure of AlCl3 squared. So we need to find out the partial pressure of our product and then also the partial pressure of our reactant. So how do you calculate partial pressure? Well, the partial pressure of your compound is just going to be the mole fraction of that compound times the total pressure in the system. So let's calculate the partial pressure of your product. So the partial pressure of Al2Cl6 is going to be the mole fraction. Let's look at our diagram here. So what's the mole fraction of these bigger compounds? Well, you have 3 of the bigger compounds and 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. So a total of 10 molecules. So that's going to be 3 over 10 times the total pressure, which is 22.1 atmospheres. So the partial pressure is going to be about 6.63 atmospheres. And let's do that same process for the reactant. So the partial pressure of aluminum chloride is going to be the mole fraction, which it has to be 7/10 times 22.1 atmospheres, and that is about 15.5 atmospheres. So let's plug that into our expression here. So 6.63 over 15.5 squared, and let's do that out. So let's do 6.63 over 15.5 squared. That is about 0.0276. And that is your answer. That is the KP. And that was question 2. I hope that was helpful. I hope you were able to learn something. I have the rest of the questions in a playlist. They should pop up on screen. Thank you for watching, and I'll see you later. Peace.